Hello students. Let us begin with an exciting journey into Unit 1, Algorithms and Problem Solving. And yes, this session is going to be super important for your in-semester exams. We will not only understand concepts, but also see what kind of questions can be asked. So keep your notebooks and minds ready. Let us begin with the first question. The question is, given the fastest computer and hypothetically infinite memory, do we still need to study algorithms? Justify. Now listen carefully. Even if we imagine the most powerful computer in the world and assume that memory is never going to run out, we still cannot ignore the importance of algorithms. Why? Because a bad algorithm will still waste time, even on a supercomputer. For example, if we try to sort a list using a very poor method, it might still take years to process a very large list, no matter how fast the machine is. Algorithms are like the brain behind the solution. They decide how efficient, how correct, and how quickly the problem gets solved. So yes, we must study algorithms to improve performance, to reduce time complexity, and to solve real-world problems smartly. अब चलो, हम अपने next important topic relation between algorithms and technology पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि How can we relate algorithms to technology? Briefly explain. Now the question is, how can we relate algorithms to technology? Algorithms are the foundation of all the technologies around us. Whether it is a smartphone app, a game, a weather forecast, or even AI-based chatbots, all of them use algorithms in the background. When you use Google Maps, an algorithm finds the shortest route. When you shop online, recommendation algorithms suggest products based on your behavior. In hardware devices like washing machines or microwave ovens, algorithms decide how much time to run or when to stop. So, algorithms are not just software ideas, they are the engines that drive every smart system and modern technology. अब चलो, हम अपने next important topic evolution of algorithms पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि Briefly explain the evolution of algorithms and how they have improved computing performance. Now let's discuss Briefly explain the evolution of algorithms and how they have improved computing performance. In the early days of computing, algorithms were very basic, often written in assembly language and handled simple operations. But as technology advanced, the demand for more efficient processing grew. That is when we started developing advanced sorting algorithms like quicksort, merge sort, and searching algorithms like binary search. Slowly, algorithms were improved using mathematical principles, data structures, and logic. This evolution helped us reduce memory usage, improve speed, and handle large-scale data. Algorithms today are so optimized that they can process millions of records in milliseconds. They truly improved computing performance by making solutions faster and smarter. अब चलो, हम अपने next important topic efficiency and design issues of linear search पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि Is this code fragment efficient? We wish to use linear search only. Justify your answer. Now here's an interesting case. Consider an array of n integers which are already in sorted order. Let x be the number being searched in the array in a linear fashion. The code performs a linear search where it checks each element one by one starting from the first index. It keeps checking until it finds the number or reaches the end. Now, is this code efficient? The answer is no, not in this case. Why? Because the array is already sorted. So if the searched number is greater than the current number at index I, and the values are increasing, then the moment we find a number greater than x, we can stop the search early. But here, the code continues even if it's no longer necessary. So, even for sorted data, it does not take advantage of early termination. That makes it less efficient. Next, let's see. Does it attribute to any design issue with respect to iterative algorithm? The answer is yes. An iterative algorithm should be designed to avoid unnecessary operations. This code repeats the loop till the end, which is not optimal for sorted arrays. A better design could check for early exit if it finds a larger element than the target number, because in a sorted list, the target cannot be after a larger number. So, yes, it shows a design issue in terms of optimization. अब चलो हम अपने नेक्स्ट इम्पोर्टेंट टॉपिक करेक्टनेस ऑफ एल्गोरिदम यूजिंग लूप इनवेरिएंट पर चलते हैं। इस टॉपिक से हम एक्सपेक्ट कर सकते हैं क्वेश्चंस जैसे कि व्हाई करेक्टनेस ऑफ द एल्गोरिदम इज इम्पोर्टेंट, डिफाइन लूप इनवेरिएंट प्रॉपर्टी and prove the correctness of finding summation of n numbers using loop invariant property. Let's now discuss why correctness of the algorithm is important. Well, imagine you are baking a cake and your recipe is wrong. Will the cake be perfect? No. Similarly, if the algorithm is incorrect, the output will be wrong. We use algorithms to automate solutions, so correctness ensures that the logic and steps will always give us accurate results. Now, what is loop invariant property? Loop invariant is a condition that is always true at the beginning, during, and at the end of every iteration of a loop. For example, if we are calculating the sum of first n numbers, we start with sum equal to 0. Each time we add a number to the sum, and the loop invariant will be that at the start of every loop, the sum contains the total of all previous numbers. When the loop ends, the invariant still holds true, proving the algorithm is correct. So, loop invariant helps us mathematically prove that the logic is sound. अब चलो हम अपने नेक्स्ट इम्पोर्टेंट टॉपिक प्रूविंग एल्गोरिदम करेक्टनेस यूजिंग काउंटर एग्जाम्पल पर चलते हैं। इस टॉपिक से हम एक्सपेक्ट कर सकते हैं क्वेश्चंस जैसे कि हाउ टू प्रूव दैट एन एल्गोरिदम इज करेक्ट, हाउ टू प्रूव द करेक्टनेस ऑफ एन एल्गोरिदम यूजिंग काउंटर एग्जाम्पल, गिव suitable example. Now let's understand how to prove that an algorithm is correct. We can prove algorithm correctness using logical reasoning, mathematical induction, and loop invariance. Another way is using a counter example. That means we try to disprove the algorithm by giving an input where it fails. For example, if we claim that an algorithm works for all positive numbers, and we try it with a negative number, and it gives a wrong answer, then the algorithm is not correct for all cases. So, counterexamples are powerful in identifying incorrect assumptions in logic. अब चलो हम अपने नेक्स्ट इम्पोर्टेंट टॉपिक करेक्टनेस प्रूफ ऑफ मिनिमम फाइंडिंग एल्गोरिदम पर चलते हैं। इस टॉपिक से हम एक्सपेक्ट कर सकते हैं क्वेश्चंस जैसे कि प्रूव द करेक्टनेस ऑफ द फॉलोइंग एल्गोरिदम व्हिच फाइंड्स द मिनिमम नंबर फ्रॉम द गिवन अरे ऑफ n numbers. Now the question is, prove the correctness of the algorithm that finds the minimum number in an array. The algorithm starts by assigning the first element as the minimum. Then it goes through each element from the second position onwards. If it finds a number smaller than the current minimum, it updates the minimum. When the loop ends, the variable min holds the smallest value. This algorithm is correct because it compares every value and keeps track of the smallest seen so far. At every step, the loop invariant is that min contains the minimum of all elements from the beginning up to the current point. Therefore, it always gives the right result. अब चलो हम अपने नेक्स्ट इम्पोर्टेंट टॉपिक करेक्टनेस ऑफ फैक्टोरियल एल्गोरिदम पर चलते हैं। इस टॉपिक से हम एक्सपेक्ट कर सकते हैं क्वेश्चंस जैसे कि प्रूव द करेक्टनेस ऑफ द फॉलोइंग एल्गोरिदम which finds the factorial of a given number. Let's now prove the correctness of this recursive factorial function. The algorithm says, if the number is 0, return 1, else return n times factorial of n minus 1. Now we use mathematical induction. Base case, when n is 0, factorial is 1, which is correct. Now for induction step, we assume that factorial of n minus 1 is correct. Then factorial of n becomes n multiplied by factorial of n minus 1, which must also be correct. So the logic holds for all non-negative integers. The function also follows the standard mathematical definition of factorial, so it is correct. अब चलो हम अपने next important topic correctness of square finding algorithm पर चलते हैं। इस टॉपिक से हम एक्सपेक्ट कर सकते हैं क्वेश्चंस जैसे कि prove the correctness of this algorithm using principle of mathematical induction. Now the algorithm is to find square of a number n using recursion. The code says if n is 0, return 0, else return 2 times n plus square of n minus 1 minus 1. Let's prove using induction. Base case, for 0, the result is 0 which is correct. Inductive step, we assume SQR of n minus 1 gives correct square. Then SQR of n is 2 times n plus SQR of n minus 1 minus 1. Using mathematics, this simplifies to n squared. Therefore, the function correctly computes square of a number using recursion. अब चलो, हम अपने next important topic iterative algorithm and design issues पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि What is iterative algorithm? Explain iterative algorithm design issues using examples. Let's understand what is an iterative algorithm. It is an algorithm that uses loops to repeat a set of instructions until a condition is met. For example, calculating the sum of elements in an array using a for loop. Design issues can arise when the loop does not terminate properly or performs unnecessary steps. For instance, if a loop checks elements even after the desired result is found, it wastes time. So, we must ensure proper loop condition, exit criteria, and minimal number of steps. Good iterative design helps in writing faster and more accurate programs. अब चलो, हम अपने next important topic classification of computational problems पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि Explain the classification of computational problems with examples. Now we move to classification of computational problems. Problems are usually classified into 3 types. First, decision problems, where the answer is either yes or no. For example, is this number prime? Second, search problems, where we need to find a solution. For example, finding the name of the topper in a class. Third, optimization problems, where we try to find the best solution out of many. For example, finding the shortest path to reach school. Each problem type helps in choosing the best algorithmic approach. अब चलो, हम अपने next important topic problem solving strategies पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि Write a short note on any 4 problem solving strategies. Now let's explore problem solving strategies. First, brute force. We try all possibilities until we find the right answer. Second, divide and conquer. We break the problem into smaller parts, solve them, and combine the results. Third, greedy strategy. We make the best choice at each step hoping it leads to the best solution. Fourth, dynamic programming. We store results of subproblems to avoid repeating them. These strategies help us solve even the most difficult challenges. अब चलो, हम अपने next important topic time complexity classification पर चलते हैं। इस topic से हम expect कर सकते हैं questions जैसे कि Classify time complexities with suitable examples. Explain linear, logarithmic, polynomial, and exponential complexities. Finally, let's talk about time complexity classification. Linear time means the algorithm runs in proportion to the input size. For example, a loop that prints every element. Logarithmic time means we reduce the problem size at every step. Binary search is a perfect example. Polynomial time means time increases as a power of input, like n squared or n cubed. Sorting algorithms often fall here. Exponential time means time doubles with every new input. Solving the traveling salesman problem is an example. Time complexity tells us how well an algorithm will perform for large inputs. And with that, we have completed all the important concepts from this unit. Remember, understanding is the key, not memorizing. Keep practicing and reviewing these concepts, and you'll do great in your in-semester exams. All the best, my dear students. Hello students. I hope you are ready and excited as we now dive into Unit 2, Analysis of Algorithms and Complexity Theory. This is one of the most important units for your in-semester exams. And every concept we are going to learn now will help you score well and understand how algorithms are measured and analyzed in terms of performance. So let's begin with full energy and focus. Let's start with the question: what is best, average, and worst case analysis of algorithms? Analyze the following algorithm in best, average, and worst case. Now let's understand these three types of analysis. The best case refers to the situation where the algorithm performs the minimum possible number of operations. It is the most favorable scenario. The average case refers to the expected number of operations when we run the algorithm on random input. It gives us a general idea of typical performance. The worst case is the scenario where the algorithm performs the maximum number of operations. This is the slowest or most difficult input case. Now, we have a code for insertion sort. It starts from the first element and moves forward. For each element, it compares it with previous elements and shifts them if needed. In the best case, when the array is already sorted, no shifting is needed, so the inner loop runs only once. Time complexity becomes linear. In the average case, some elements are out of place, so some shifting happens. Time complexity becomes quadratic. In the worst case, the array is in reverse order, and every element must be compared with all the previous ones, leading to the maximum number of operations. So, again, the time complexity is quadratic. Now let's move on to our next important topic, linear search time analysis. From this topic, we can expect questions like: what is best, average, and worst case analysis of algorithms? Analyze the following algorithm best, average, and worst case. Let us now look at the linear search algorithm. This function searches for an item in an array from the beginning till the end. In the best case, the item is present at the first position, so only one comparison is needed. In the average case, the item is somewhere in the middle, so around half the array is searched. In the worst case, the item is either at the end of the array or not present at all, and the algorithm checks every element. So, time complexity ranges from constant time in best case to linear time in worst case. Now let's move on to our next important topic, limitations of best case analysis. From this topic, we can expect questions like: comment on the statement, best case analysis of algorithm may not give clear idea of performance. Now let's understand why best case analysis might not always help us. When we look only at the best case, we are assuming the most favorable input, which might rarely occur in real situations. For example, saying that linear search takes only one comparison is misleading, because in practice, the item might be at the last position or not present. So, we need to focus more on worst case and average case, which give more realistic estimates of performance. Now let's move on to our next important topic, understanding behavior of algorithm cases. From this topic, we can expect questions like: what do you understand by best case, worst case, and average case behavior of an algorithm? Is an average case efficiency an average of best case, worst case efficiencies? Justify answer. Let's explore this now. The best case is when the algorithm runs with the least operations. The worst case is when it does the most. The average case is not simply the average of these two. Instead, average case is calculated using probability and total number of operations on all possible inputs. So, it depends on the input distribution and requires deeper analysis. Hence, average case is more complex and not a simple mean of best and worst. Now let's move on to our next important topic, dominant operations in time complexity. From this topic, we can expect questions like: explain the role of dominant operations in analyzing time complexity of an algorithm with an example. Dominant operations are the steps in an algorithm that are repeated most often or that take the most time. When we analyze time complexity, we do not count every instruction. We focus on the operation that affects the total time the most. For example, in a sorting algorithm, comparisons and swaps are dominant operations. If we count them, we get a good estimate of performance. So, identifying the dominant operation helps simplify complexity analysis. Now let's move on to our next important topic, meaning of O and omega for SAM function. From this topic, we can expect questions like, if an algorithm has a time complexity of both big O of f of n and omega of g of n for the SAM function f of n and g of n, then what does it imply? Explain. If both upper bound and lower bound of time complexity are the SAM function, then it means that the function is tightly bound. That means the algorithm always performs close to that function, whether best or worst case. For example, if both big O and omega are n squared, it means the algorithm takes time around n squared for any kind of input. Now let's move on to our next important topic, understanding big O, omega, and theta notations. From this topic, we can expect questions like, what do omega and theta notations mean? When do we use big O notation? Big O notation represents the upper bound of time complexity. It tells us how the time grows in the worst case. Omega notation is the lower bound and shows the best possible time. Theta notation gives a tight bound, meaning both lower and upper bounds are the SAM. We use big O most commonly, especially when estimating maximum possible time an algorithm will take. Now let's move on to our next important topic, implications of big O relationship. From this topic, we can expect questions like, if f of n is big O of g of n, then does it imply g of n is big O of f of n? Discuss. Now listen carefully. If f of n is big O of g of n, it means f grows no faster than g. But this does not mean that g is big O of f, because g might grow faster than f. For example, n is big O of n squared, but n squared is not big O of n. So the implication does not go both ways. Now let's move on to our next important topic, theta analysis of polynomial expressions. From this topic, we can expect questions like, is 6n cubed equal to theta of n squared? Justify your answer. Let's understand this clearly. Theta of n squared means the function grows like n squared, but 6n cubed grows faster than n squared. So, no, 6n cubed is not theta of n squared. It is big O of n cubed and not theta of n squared. Now let's move on to our next important topic, selection sort time complexity analysis. From this topic, we can expect questions like, analyze the complexity of this algorithm. Clearly indicate the assumptions made, if any. The given selection sort algorithm selects the minimum element from the unsorted part and swaps it with the current position. For each element, it compares with all remaining elements, so the outer loop runs n times and the inner loop runs up to n times as well. Hence, total number of comparisons is roughly n squared. No matter how the array is arranged, the number of comparisons remains SAM. So the time complexity is quadratic in all cases. Now let's move on to our next important topic, polynomial time reducibility. From this topic, we can expect questions like, what is polynomial time reducibility? What is its importance in computational complexity theory? Polynomial time reducibility means we can transform one problem into another in polynomial time. This helps in classifying problems. If we can reduce a hard problem to another one and solve the new one efficiently, then we can solve the original problem too. It helps in understanding relationships between problems and proving their complexity classes. Now let's move on to our next important topic, deterministic versus non-deterministic algorithms. From this topic, we can expect questions like, differentiate between deterministic and non-deterministic algorithms with examples. Deterministic algorithms always produce the SAM output for a given input and follow a fixed sequence of steps. For example, binary search is deterministic. Non-deterministic algorithms can follow multiple paths and may produce different outputs. For example, solving a puzzle by trying many possibilities is non-deterministic. These are mostly theoretical and used in complexity theory. Now let's move on to our next important topic, P and NP problems. From this topic, we can expect questions like, briefly explain P and NP problems in the context of complexity theory. Give suitable example. P problems are those which can be solved in polynomial time by a deterministic algorithm. NP problems are those whose solutions can be verified in polynomial time by a deterministic algorithm. For example, multiplying two numbers is a P problem. But checking whether a number is a product of two prime numbers is an NP problem. The big question is whether P equals NP. Now let's move on to our next important topic, understanding P, NP, NP hard, and NP complete. From this topic, we can expect questions like, explain P, NP, NP hard, and NP complete problems with examples. P is the set of problems that are solvable in polynomial time. NP is the set whose solutions are verifiable in polynomial time. NP hard problems are at least as hard as NP problems, but may not belong to NP themselves. NP complete problems are both in NP and NP hard. An example of NP complete is the traveling salesman problem. Solving it quickly would mean we can solve all NP problems quickly. Now let's move on to our next important topic, vertex cover problem. From this topic, we can expect questions like, what is NP complete class problem? How would you prove vertex cover problem is NP complete class problem? The vertex cover problem asks us to find the smallest set of vertices such that every edge in the graph has at least one endpoint in that set. This is NP complete because it can be verified quickly and other NP problems can be reduced to it. Proving NP completeness involves showing that it is in NP and that an already known NP complete problem can be reduced to it in polynomial time. Now let's move on to our next important topic, 3-set problem and its importance. From this topic, we can expect questions like, explain 3-set problem using an example. Why is a set so important in theoretical computer science? 3-set is a special version of the satisfiability problem where each clause has exactly 3 literals. The question is whether there exists a combination of true and false assignments to variables such that the entire expression becomes true. For example, given 3 clauses like A or not B or C, not or B or D, and E or not D or C, can we find such values? It is important because many complex problems can be converted to SAT, making it central in theory. Now let's move on to our next important topic. Proving 3-SAT is NP complete. From this topic, we can expect questions like, what is SAT and 3-SAT problem? Prove that 3-SAT problem is NP complete. SAT is the general satisfiability problem. 3-SAT restricts each clause to have 3 literals. We can prove that 3-SAT is NP complete by showing that SAT can be reduced to 3-SAT in polynomial time and that 3-SAT belongs to NP. Hence, it satisfies both conditions for NP completeness. Now let's move on to our next important topic, Hamiltonian cycle and NP hardness. From this topic, we can expect questions like, what is Hamiltonian cycle problem? Why is it considered NP hard? Explain with example. The Hamiltonian cycle problem asks if there is a cycle in a graph that visits every vertex exactly once and returns to the starting point. It is NP hard because no polynomial time algorithm is known for it, and solving it would solve many other difficult problems. An example would be visiting each city once and returning home with minimum travel. This makes it a hard problem in complexity theory. And with that, we have covered all the major concepts and questions from this unit. These topics are not only exam-focused but also help you understand how powerful and essential algorithms are. Keep practicing, stay confident, and you'll definitely succeed. All the best, my dear students.